Okay, here in example 2, we want to try to use a Pythagorean triple to find the value of x. This is basically saying we're gonna use sort of like our list of common triples to avoid using the Pythagorean theorem and going through that a squared plus b squared equals c squared. We're going to try to identify when you can skip that step. It doesn't happen very often, but occasionally you can, and this is going to be an example of that. So if we have 14 and 50 and x, and we want to say, is this a Pythagorean triple? Well, we've got a list of like these 4 triples. Now, I find this kind of not super useful because they don't come up that often, and really the only one I remember is 3, 4, 5, just because those numbers are really easy to remember. They're just 3 numbers in a row, 3, 4, 5. These other ones are a little trickier, like there's no clear pattern here, 5, 12, 13, 8, 15, 17, 7, 24, 25. They're not quite as easy to remember, but we're going to try one out. So here we have 14 and 50. It says that, notice that 14 and 50 are both multiples of 2, because we have 14 is 2 times 7, and 50 is 2 times 25. So that 7 and that 25 are part of a Pythagorean triple, which means that the missing piece would have been 24. Well, since these are not a 7, 24, 25 triple, they're a multiple of that. They're twice as big. We're not going to have 24 here, just like we didn't have 25 up top. We had 50. Instead of 24, we are going to have 48. Okay, so 14, 48, 50 is just twice as big as this one. So remember that with these Pythagorean triples, you can use these numbers themselves, or you can increase the numbers by some multiple. So if we want to do 3, 4, 5, we could. We could also do 6, 8, 10. We could do 9, 12, 15. We could do you could skip all the way to 30, 40, 50. Okay, so we can do those kind of multiples. So on this one, we want to figure out what our multiple might be. So I'm going to say that I can reduce this. Well, if we cut it in half, it'd be 24 and 10. That wouldn't be the smallest we could get it. We could then go to 12 and 5. Well, I see 12 and 5 here. So I think we have a 5, 12, 13. Okay, so I'm just going to look here. Well, 5 times 4 is 20. 12 times 4 is 48, and 13 times 4 would be 52. So I think this missing side would be 52. Okay, so like I said, I don't know that these are the most useful things to memorize because in general, you can figure these things out using the Pythagorean theorem anyways. We didn't need to use these triples to do it. I could have just said a squared plus b squared equals c squared. It's just that if these kind of stick in your memory, you can identify certain cases where you can skip that step. I would say the only one that I would ask you to try to memorize is the 3, 4, 5 triangle. 3, 4, 5, and any multiples of 3, 4, 5. That's the easiest one to remember. And it's a good one to draw out when you're trying to remind yourself of why the Pythagorean theorem works. If you can remember the numbers 3, 4, 5, then you can say that, okay, 3, 4, 5. 3 squared is 9. 4 squared is 16. 5 squared is 25. And you can come up with a quick example where when you add the squares of the shorter sides, you total up to the square of the larger side.